Hello again. In this part of the course, we're going to focus on the statistical applications of NumPy arrays. We're going to examine how to use NumPy's native statistical functions and methods and discuss why we prefer using them compared to Python's own equivalent versions. Then we'll go over some fundamental functions, like min and max, before jumping in with several statistical order functions. Afterwards, we'll examine the many ways to compute averages and variance before moving on to covariance and correlation between several arrays. After we've done that, we'll move on to histograms and comment on their importance in understanding data distributions. We'll wrap up our trip through the statistical applications of NumPy as we talk about NaN equivalents of functions and why they're so very useful. So now that we have our roadmap ahead of us, let's begin. Before we jump into Python though, we'll make a quick detour through NumPy's documentation. Open up an internet browser of your choice and go to numpy.org. From the homepage, click on Documentation on the top right side of the page. This will transport you to the documentation page, where you can find information on anything NumPy related. The version you see in the middle of your screen will always be the current latest version. At the time of recording this video, it is apparently 1.19, but the one you see in your browser will very likely differ. That's because NumPy is often being updated, so most probably there will be a newer version of it by the time you are watching this video. However, there's no reason to panic, since the documentation page has pretty much stayed the same over many iterations of NumPy. Hence, we can just go to the search bar and type in statistics. Among the top results should be a page titled Statistics. If we click on it, we'll be redirected to a page with links to all stats-related functions in NumPy. For your convenience, they're already split into 4 major topics: order statistics, averages and variances, correlating, and histograms. We'll have a close look at most of the functions listed here, but if you're ever uncertain of the syntax of a function, you can always revisit this page on your own. Fantastic! In this lecture, we're going to examine how to fully take advantage of NumPy's mean function. So let's get back to Python and start by importing the package. All right, next on the agenda is generating an array to plug into the function. As you know, 2D arrays are equivalent to matrices, so we'll call our variable matrix A. We'll set it equal to np.array and plug in a list of lists for its initial values. For most of this section, we'll be reusing the same matrix over and over. So if you want to get the same results as us, you can just create the exact same 3x5 matrix like the one we're currently writing out on screen. Good practice dictates displaying the variable to make sure we've defined it correctly. Everything looks okay, so we can continue. Call npmean and only plug in matrix A without adding anything else. The output is a single value which depicts the mean value for the flattened array. The flattened part comes from ignoring the shape of the array and flattening it down to a long one-dimensional array along its main axis. Therefore, 3.4 is the arithmetic average of all the values in the array. The result is computed by adding up all the elements and dividing it by the number of elements. To further practice this concept, what if we weren't interested in knowing the mean of the entire data, but only the first row? Well, we can use indexing to only pass the first row of the dataset as an input of the function. We can do so by adding bracket 0 bracket after matrix A. And in this way, we won't refer to all elements of the matrix, but just those in the first row. The new output is 1.0. So despite the result being an integer, it's still displayed as a decimal. That's because the default data type, even for integer inputs like the ones we have, is actually float 64. Therefore, although you see integers in our matrix A array, NumPy treats them as floats. We can also quickly check the accuracy of the function, since we have the matrix displayed above. The 5 elements of the first array have a sum of 5, so 5 divided by 5 gives us the same output, 1. Next up, we can also call this method on a column rather than a row. Once again, we can use indexing to help us achieve this. Simply insert a colon and a comma after the opening squared bracket. The result is 2.6 repeating, which once again makes sense since the 3 elements of the first column add a sum of 8, and we know that 8 over 3 is exactly 2.6 repeating. Even though this works just fine, it would be extremely slow if we needed to compute the means for every column of a big data set one by one. Lucky for us, we don't have to. Instead, we can pass the entire array without indexing, and instead set the axis argument to 0. The output is an array of 5 values, where each one is the mean value of its equivalent column. The 2.6 repeating we see in the first position matches the mean of the first column we calculated earlier. Hence, specifying an axis argument allows us to compute several means simultaneously. Nice! As you might expect, if we change the axis argument from 0 to 1, we'll no longer be finding the means for every column, but rather the means for every row. Let's try that out. The output consists of an array with only 3 values, 1 for each row. We won't bother double-checking every one of them, since we already know the first one is accurate, but you can check the numbers on your own if you want, of course. Great! It's no secret that NumPy also contains many methods, which are equivalent to the functions from the standard Python library. For example, typing matrix A.mean gives us the exact same result as calling the function on the flattened array. If the outputs are identical, then why do we prefer using the functions? Well, the answer is abundance. Simply put, there are more statistical NumPy functions than methods, which means not all functions have equivalent methods that perform the same task. Take NP sqrt for example. It's a function that finds the square root of every element within the array. However, if we type in matrix A.sqrt, we get an attribute error because no such method exists. Thus, to keep the code consistent throughout the course, we'll stick with functions wherever convenient. Additionally, functions like npmean possess the same features as universal functions. Hence, they can be broadcasted, called over specific axes as we saw earlier. Or we can even typecast the outputs, meaning we can control what the results look like every time we use them. For example, if we call npmean along the first axis and set the data type argument, dtype, equal to np int 64, we'll get integer approximation for all the values in the array. This, along with the ability to define other keyword arguments, makes NumPy's functions the superior choice. In the remaining lectures of this section, we'll try to avoid going over broadcasting or typecasting examples, since you've seen how to use both already. All right. Now that we know how and why to use NumPy's statistical functions, we're ready to start exploring some of the more useful ones. In the next lecture, we'll focus on finding the minimum and maximum within an array. Thanks for watching.